To start this lesson off, let's just go ahead and see where we're at in the scope of the entire unit, the entire chapter of material. So what we've already covered at this point is we've already talked about the top two. So we've already talked about function operations and defining what an inverse is. Where we're at now is we want to define exponential functions. What is an exponential function? And then we also want to look at how is this used in real life. And so that's what we want to focus on in this lesson is to say, what is an exponential function? How do I graph it? How do I solve some basic equations with it? And then when is it actually used in real life? And so again, where we're going with this then is then to say if I know what an inverse is, and I have this really useful function, this exponential function, then I should probably be able to undo this useful function in order to solve equations that involve this useful function. So after this, we'll then define what the inverse of this exponential is and look at how that behaves. And in the end, we're then going to say, let's wrap it all together and say, how do I solve these exponential equations that could come up in lots of real life situations? So that's where we're going with this. So let's start off with just a basic definition on what this exponential function is. And as we progress through this lesson, we'll start to see where it's going to be so applicable in real life. So we're going to define the exponential function as a function of the form f of x equals b to the x power, where the b, which is called the base, our base needs to be strictly bigger than 0 and not equal to 1. So what we mean by this then is that we don't want to have 0 to the x power. We don't have a negative number to the x power. We don't have 1 to the x power. But what an exponential function could look like is it could look like 2 to the x power or 3 to the x power. We could allow fractions that are in between 0 and 1 as well, so we could have something like 1/2 to the x power. So this is what we mean by what an exponential function is. And the x, of course, is a real number but we're treating it like a variable for now. So an exponential function is going to have a numerical base that's given to us where we know the number. But the exponent is where the variable is. So y equals, or f of x equals, some number that we know raised to the x power. Now, of course, we're going to start looking at slight modifications to this. We might have to the x plus 1 power or something like that. So the way we're going to explore this is we're going to start off looking at graphing these things. Once we're done graphing them, then we can start to look at how they behave in different ways, like equations, and then also how we could turn some applications or word problems into them. So that's kind of where we're going with this, but here's our basic definition on what an exponential function is so it can be used in the right vocabulary. So let's start exploring these exponential functions by graphing them. And these first couple examples aren't necessarily how I exactly want you to graph them in the end. So we can think about this more like an intro, how in this course we've had some example intros where I sort of walk you through the learning process, and then we get to an example where we actually do it. So think about this more like an intro. We're going to explore this exponential function at first. So when we're faced with a new function that we want to graph, typically what we want to do is set up our XY table and start plugging numbers in. And it's a good idea to plug in 0, some negatives, some positives, and just see where that takes us. So I'm going to start off with 0, 1, 2, and 3, as well as -1, -2, -3. And if we have to look at more than that, that's great. We can see where this thing's going, start to get some ideas of what's happening with these values. If we end up needing to look at fractions, we can do that as well. But start in the middle with 0. If I plug in x equals 0, then I'm talking about 2 to the 0 power. And anything to the 0 power is 1. I want to repeat that. Anything to the 0 power is 1. I wanted to repeat that because let's take a step away from this particular example for a moment and let's think about our general exponential function of b to the x, where we don't know what b is. F of 0, or b to the 0 power, is always going to be 1, meaning the ordered pair 0, 1 is on the graph no matter what. So unless we've done some shifts left, right, up, or down, that kind of thing. But as long as there's no shifts, as long as we're looking at an exponential function of the form b to the x, 0, 1 is always going to be on the graph. And all that's really saying is anything to the 0 power is 1. It kind of goes back to that rule. So that's kind of cool anyhow. All right, so let's look at what happens when I plug in x equals 1, or in other words, when we look at f of 1. So when I look at f of 1, I'm going to have 2 to the first power, which is just 2. Okay. Well, let's look at what happens when we let x equal 2, or in other words, when we take f of 2. I'm going to go ahead and come get the graph off the screen a second so we can just write. When I want f of 2, keeping in mind I'm going to write this on this part of the screen so we can remember what we're doing here. We have 2 to the x power. If my x that I'm plugging in is 2, then I have 2 squared. 2 squared is 2 times 2, which is 4. What if x is 3? So f of 3 would be 2 cubed, which is 2 times 2 times 2, which basically means take my 4 that I got from the last one and multiply by 2 one more time. That gets me 8. So just in the sake of pattern finding, I do want to look at x equals 4 so you can start to see what's really going on here. If I have f of 4, which is 2 to the 4th power, 2 to the 4th power is 2 times 2 times 2 times 2. Well, from the previous problem that I did, I know that 3 of these guys are 8, and I'm just multiplying by 1 more 2. So I want you to notice what happened each step of the way. As I went from plugging in a 1 to plugging in a 2 to plugging in a 3 to plugging in a 4, each step of the way the y value doubled. And it doubled because I took the previous answer and multiplied by my base one more time. That's what was going on in these problems. As you go from a base to the first power to the base to the second power, you're multiplying by that base one additional time. As you then go to the base cubed, you're multiplying by the base one additional time. Base to the 4th, take that previous answer and multiply by the base one more time. That's what's going on here. So you can see since our base was 2, we're doubling every step of the way. We're multiplying by 2. Which means if we were going to the left, if we were taking a step backward, we'd be multiplying by 1 less 2. Or in other words, we'd be dividing by 2. And as we start to plug in negatives, we're going to see that that is exactly what happens. When I plug in x equals negative 1, that's 2 to the negative first power, which is 1 over 2. I took my previous answer of 1, and I divided by 2. If we look at x equaling negative 2, or f of negative 2, that's 2 to the negative 2, or 1 over 2 squared. So again, I divided by 2 again, or in other words, I multiplied by a half. I took half of it. And sure enough, if I look at x equals negative 3, where I'm taking f of negative 3, that's 2 to the negative third. That's 1 over 2 times 2 times 2. I divided by 2 one more time. So let's see what this looks like on the graph. The first ordered pair that I found was the 0, 1. I took a step over and I doubled that to get 2. Took another step over, doubled that to get 4. Took another step over, doubled that to get 8. Took another step over, doubled that to get 16. Now going back to 0, 1, if I took a step to the left, I took half of that 1. Another step to the left, and I got half of that again. Another step to the left, I got half of that again, down to 1/8. And if I kept going, I would get 1/16, then 1/32nd, then 1/64th, then 1/128th, then 1/256th, then 1/512th. Each step to the left that I take, I get half the distance to 0. Half the distance to 0. Now, because I'm cutting that distance in half each time, I'm never going to get down to 0. I'm going to get close, but I'm never going to touch the x-axis. So what's actually happening with this graph here, if I connect my dots, sorry for the little bit of a squiggly line, it's not the straightest thing in the world, I'm going to keep getting closer and closer and closer and closer to this x-axis, but I'm never going to touch it. It's what we call an asymptote. We're going to get closer and closer and closer to that x-axis as we go to the left, but never touch it, which means we're never going to have a negative number. We're never going to have a negative y value. We're also never going to have a 0 y value, which should make sense that we can't take a positive number like 2, raise it to a power, and get 0. We can't do that. We can't take a positive and raise it to a power and get a negative either. So it makes sense that all the y values, all of our answers, are positive numbers. Now in this example, we're going to walk through it a little bit faster than we walked through the previous example of graphing an exponential function, because hopefully we're starting to get the idea of how these things work. So what I want to do first is I want to remember the fact that we said is that we can always start at the ordered pairs 0, 1, because anything to the 0 power is 1, even though we have a fraction base here. So I'm going to scroll down over here and say, let me put an ordered pair at 0, 1. We at least know one ordered pair. And then every step I take to the right, multiply my previous y value by the base. That's what we were doing when we were looking at 2 to the x. We said every time I introduce a new x, the exponent increases by 1. If I increase the exponent by 1, what that means is multiply by the base 1 additional time. Let me repeat that. Every time we increase the exponent by 1, that means to multiply by the base 1 more time. That's not a super deep thing. That's the definition of what an exponent is. An exponent says this is how many times I multiply by my base. So if I increase my exponent by 1, then I'm saying multiply by the base 1 additional time. So as far as this problem, when the x value was 0, the y value was 1. So if I increase my x value by 1, then I'm going to multiply 1, I actually write 1 times. My base is 1/3, so I'm going to take the previous y value and multiply it by 1/3. That's 1/3. So I'm going to plot that. If I take another step to the right so that my x value is 2, I take my previous y value and multiply it by 1/3. That gets me 1/9. So I'm getting really close to the x-axis is what's happening here. And similarly, if I went to x equals 3, I would take my previous y value and multiply by 1/3 to get 1/27th. Really, I mean, at this point, I'm like super duper duper close. So we just know that we're getting close to the x-axis, but we are still decreasing. That's important to realize. Now, we'd also said on the last example that if I decide to go to the left instead, so let's write this out. So every step to the left, we said that we're going to multiply by 1 less version of the base. But to multiply by one version less means to divide. That's what division is. It's undoing multiplication. So if I take a step to the left, I'm going to divide my previous y value by my base. So going back over here, if I take a step to the left, that means I'm going to go to -1 from 0. My previous y value was 1. If I divide by my base, remember that division by a fraction is the same thing as multiplying by the reciprocal. So I'm really multiplying by 3. So my y value should be 3. If I take another step to the left where x is -2, then I'm going to take my previous y value and divide by 1/3, which means multiply by 3. And that gets me 9. And so I can see that if I were to take one more step to the left, my y value would be 9 times 3, which is 27. Now I can't put 27 on my graph, but it's important to know this value 27, because when I continue my graph, I don't want to make it look like this, where I'm crossing through at about 10.5. That would be wrong. I know that my graph should be really, really steep here, because I'm aiming up for 27, which is way off the graph. So it kind of gives me an idea of how steep my graph is to know that value. So as we look at these two examples that we just did, I want you to notice a couple things. So besides what we wrote as far as those 3 steps, I want you to notice that in both cases, these are one-to-one functions. They pass the horizontal line test. And we know that because in this case where we had a base that was a fraction, we were always decreasing. As you went left to right, you were always going downhill. So we're never going to pop back uphill to hit the same y value. Same thing when our base was bigger than 1, we are increasing. So as we are increasing here, we're never going to hit the same y value again. So we know that in either case, this is a one-to-one function, which is important so that we know there is an inverse. An inverse exists here. That kind of motivates our whole next lesson beyond this when we start to talk about the inverse of the exponential being the logarithm. Now also, I'd mentioned it already, but I just want to point it out again, that when our base was bigger than 1, we were increasing. We were going uphill. When our base was less than 1, we were going downhill. And that should make sense when we look at this second step here. That when to go to the right, we multiply our previous y value by our base. If our base is bigger than 1, then the y value is getting bigger. If that base that we multiply by is less than 1, then we're making that number smaller. So if your base is bigger than 1, you're increasing. If your base is less than 1, you're decreasing. So I know we wrote it out on the previous example, but I just want to make sure it's right here in your notes and spelled out nicely on the screen in nice typed out versions, because this is how I want you to think about graphing an exponential function. That if we want to graph the exponential function b to the x, then we know the ordered pair 0, 1 will definitely be on the graph. If you want to take a step to the right by 1, so you're increasing your exponent by 1, you're going to multiply the previous y value by your base. When you take a step to the left by 1, you're decreasing your exponent by 1, so you're multiplying by one less version of the base, or in other words, we're going to divide the previous y value by the base. One of the reasons I want you to know this process here is because it's going to allow us to graph logarithms really easily if we really understand this process. Because if we understand that logarithms are just the inverse of the exponential, inverses mean to flip-flop ordered pairs. So we're going to say, hey, the ordered pair 1, 0 must be on a logarithm. And if we're flip-flopping the ideas of x's and y's, then a positive x direction is going to flip into a positive y direction, which would be up. And y values would switch into x values. And similarly, when we look at the word left, which is a negative x direction, that would shift into a negative y direction or down. That y value would turn into an x value. So we can basically have a process to graph logarithms if we understand this process for graphing exponentials, that we're just going to flip-flop the ideas of x's and y's because that's what an inverse is. Now we're not doing that yet. That's going to be in the next lesson, but I just want to point out why I want you to think in this kind of process way, is it really does help us to understand how to do a logarithm then. So now let's look at a shift. So in this graph, we're supposed to be graphing 3 to the x plus 2. That plus 2 is directly next to the x, meaning the shift is to the left 2 units. So what I want you to do when you're faced with a shift like this is I want you to say, if I'm going to shift to the left 2 units, let me take my entire axis and shift the axis to the left 2 units. So that now what I have highlighted in yellow is my new x and y axis. Now my x-axis didn't shift at all, but now the y-axis shifted to the left 2 units. And then once we've shifted to the left with this new set of axes, we can just graph a regular old 3 to the x. How do we graph a regular old 3 to the x? We start off at the ordered pair 0, 1. Now ignore the labels that are there and just graph relative to this axis. Where I've plotted is 0, 1. Then, if I take a step to the right, multiply the previous y value by my base of 3. So my previous y value was 1. I'm going to multiply by 3. That gets me 3. If I take another step to the right, so this was at x equals 1. So if I take another step to the right, then I'm going to take my previous y value and multiply by 3. That gets me 9. If I want to take another step to the right, now keep in mind these x values are relative to the new axis. I'm going to take my previous y value of 9 and multiply by 3. So this is one of those off the charts values. So we know that this thing is really steep there and continues going really steep. Now if I want to take a step to the left, I'm going to divide the y value by 3. So I'm going to go back over here to my 0, 1. I'm going to call it 0, 1, even though I know it's at -2. We're looking relative to my new axes. If I take a step to the left, then I'm going to take the previous y value, which was 1, and I'm going to divide by 3. That gets me 1/3. If I take another step to the left, I'm going to take that 1/3 that I had and divide by 3 again, or in other words, multiply by 1/3 to get 1/9. And we know we're just going to keep on getting closer and closer and closer to the axis. So we can continue this line, get super close, and there we go. So that's how we want to do a shift, is we want to shift where the axes are. And we could do similar, that if we had, for instance, off to the side here, I'll do this. So suppose we had 3 to the x plus 2 here. That would be a shift up by 2 units. So if we took our normal axes, I would make my new axis 2 units up from there. And then I would graph 0, 1 from that new set of axes there. All right, so let's shift gears away from graphing for a minute and let's talk about equation solving. Now, I'd mentioned in one of the previous portions of this video that I wanted you to notice that exponential functions were one-to-one. They passed the horizontal line test. So for that reason, that tells me that my y values are unique. Or in other words, the exponential function is a unique function. This uniqueness, or invertibility, because it's one-to-one, gives me a really cool fact and a really cool way of solving some exponential equations. It tells me that if I have two different exponential functions that are equal, so if I have b to the x equaling b to the y, where the bases are the same, so I have 2 to the x equals 2 to the y, or 5 to the x equals 5 to the y, then it tells me the exponents must be the same. So if the bases are the same, then the exponents must also be the same, is what it's telling me. This allows me to solve some exponential equations by saying if I can make the bases the same, then the exponents must be equal too, and then I can solve the equation of the exponents being equal. So let's look at an example of how we could use this to solve some equations. So we're going to start relatively simple and build ourselves up to some pretty cool equations that we can actually solve using this uniqueness of the exponential. So remember, the goal with the uniqueness of the exponential is to have an exponential on the left and an exponential on the right that have the same base. That's really important. So we want to write both sides of the equation as an exponential with the same base. So in this first example that I have 2 to the x, the goal is to rewrite 16 as 2 to some power. So 16 could be written as 2 to the 4th power. That's what it's equal to. The uniqueness property of the exponential now says because I have this equality of exponentials where the bases are the same, then the exponents must also be the same. And I can just set them equal to each other. In this case, x must equal 4. And that solves the equation that we've solved for x. Now where things get a little bit trickier is in this next one. Don't write this down. If I try to do the exact same thing and say 27 is 9 to what power? Well, I know 9 to the first is 9. I know 9 to the second's 81. Somewhere in between them. Now, if you're really good with your rational exponents, you might know the answer to this. But I would rather show you a way that we don't have to be really good with our rational exponents, because rational exponents are kind of hard. So instead of writing the left side as 9 to a power, let's instead write it as 3 squared. So 9 is 3 squared, but when you raise a power to a power, you multiply the powers. And so really we can think about that as 3 to the 2x. And so that means on the right-hand side, I want to rewrite this as 3 to a power as well. So how do I rewrite 27 as 3 to a power? Well, that's actually easy. That's 3 cubed. The uniqueness property now tells me, since my bases are the same, my exponents must be the same as well. So 2x must be the same thing as 3. So now in order to solve this equation, I can divide both sides by 2 and get that x equals 3 halves for that example. Now you can obviously check your answer too. You can actually take 9 to the 3 halves power and make sure you get 27. Just keep in mind if you're putting this into a calculator that if you put in 9 to the 3 halves, that the calculator is going to do order of operations properly, which would be take the exponent and get an answer, then divide that answer by 2, which isn't what you intend. So if you did want to put this into a calculator, parentheses are important to say the 3 halves is the entire exponent, so it needs to be in parentheses. So let's go ahead and look at 3 more examples of the same idea of using the uniqueness of the exponential, and just situations are going to get a tiny bit trickier at each step. For this first example, both sides have an x to them. Now, I don't know how to rewrite 8 as 4 to a power, but I can go ahead and try to find a common one by saying 4 is 2 squared. Eight is 2 cubed. So again, when you raise a power to a power, you multiply the powers. So really my powers are 2 times x plus 3 and 3x. And in both cases, the base is 2. So because both bases are 2, I can look at just the exponents and say those exponents must be equal. And then solve this equation. So to solve this, we distribute. I'd subtract the 2x to the other side. So x is 6. Moving on to the next example. Now this one, look at where the x is at. Where the x is at is typically going to be our goal base. So we have 3 to the 2x. 3 is already pretty much as good as we're going to get. So then we look at the left-hand side and say, I want to rewrite him as 3 to a power. Now the fact that he's a fraction tells me I want a negative power, because negative means take the reciprocal or put it on the bottom. So we know it's negative, and then 3 to the third power is 27. So that's what we got to remember about powers, is that negative powers mean to take the reciprocal. Now that my bases are the same, I can set the exponents to be the same. Then I can divide by 2 to get the x by itself. And there we go. Now, one other minor example that I didn't actually put into the notes, but let's just do it real quick, is to say, what if I had something like 2 to the 3x equals, let's say, 1. Same deal, that I want to write this as 2 to some power. How do we rewrite 1 as 2 to a power? Anything to the 0 power is 1. Now that my bases are the same, I can make the exponents the same, divide by 3, and x must be 0. So don't forget that fact. So we have 2 important facts about exponents to remember: that a negative exponent means to take the reciprocal. So if you're trying to solve these problems by saying, what exponent do I need to make this guy a fraction? It needs to be negative. If you have a 1 on the other side, what exponent do I need to rewrite 1? You need an exponent of 0 to turn something into a 1. All right, last portion of this example. 4 equals 3 to the x. So if we kind of do the same thing of saying 3 to the x is as good as I can get, so I know that I need 3 to some power. 3 to what power gets me 4? How do I do that? I don't know. That's the point of why we need to be able to undo an exponential. I can't use the uniqueness of the exponential to solve that equation there. I can't rewrite 4 as 3 to a power. 3 to the first is 3, 3 to the second is 9. It's somewhere between there. It's somewhere between 1 and 2, but I don't know. I really don't. So I need a way to undo 3 to a power. I need to undo the exponential function of 3 to the x. That's what I need to be able to do, and that's why we're going to continue on in this unit and talk about the inverse of the exponential. We'll eventually come back to this problem and we'll be able to solve it. Then we'll learn how to put it in the calculator to get some sort of decimal approximation to it. But for now, we just don't know. So, just to take a step back for a second and look big picture. What I've shown you in these last two examples of solving exponential equations using the uniqueness of the exponential, this is a very specialized version of solving exponential equations. It only works in certain circumstances. It only works if we can write both sides with the same base. So this is similar, not the same, but similar to when you're solving quadratic equations, that if your quadratic was factorable with the other side 0, that was easy. So it's something that you always look for and say, let me start every problem off looking to say, can I factor it? If I can't, I'm going to use the quadratic formula. When we get to using logarithms to solve exponential equations, we're going to use similar reasoning. We're going to say, well, let me see if that easy stuff that I learned early on works. Let me see if I can write both sides with the same base. If I can, awesome. But if I can't write both sides with the same base, that's when I then need to say, all right, let me break out the big guns. Let me use this logarithm thing. But for now, we're going to try to make both bases the same. All right, so now we're going to get into a couple of word problems that utilize exponential functions. But before you freak out, I do want to tell you that these couple examples, the next couple, are like the easiest word problems that we're going to deal with, period. They're really just plug and chug type of problems. There's a couple little caveats you got to be careful of. But let's go ahead and read through this one. The size of the rat population of a wharf area grows at a rate of 8% monthly. If there are 200 rats in January, find how many rats, round to the nearest whole, because we don't want portions of a rat, should we expect by next January. And use the equation 200 times 2.7 to the 0.08t. Now, the one thing I just got to tell you about equations that come with these exponential functions is the big thing we got to be careful of is to make sure that our units match up. That when we're talking about a monthly rate, then the time that we plug in needs to match up. It needs to be that many months. So if we're going January to January, that's 1 year, that's 12 months. So what this problem is really asking us is when your t value is 12, how many rats do we have? And so really this is as simple as saying y equals 200 times 2.7 to the power of 0.08 times 12. Notice that the right-hand side is all numbers. There's nothing to solve. It's just plug this into the calculator. So like I was saying, these really are going to be some of the easiest word problems that we ever deal with. So let me go ahead and get our calculator out, and let's take a look. So to type this into our multi-view calculator, we have 200 times 2.7. And this is where we really start to see the beauty of the multi-view calculator, is that when I raise to the power, I don't need fancy parentheses or anything. I'm just going to say 0.08 times 12. I can clearly see that it's all in the exponent, so the calculator is understanding the same thing as what I'm trying to type in. I hit enter and I get this answer of 518.966. So it's up to you on how you write your answer. I would actually accept on this 519 rats. I would accept 518 rats as an answer. 519 is probably better. The reason I would accept 518 is because I could see the reasoning that we haven't achieved our 519th rat yet. And so there are still 518 whole rats. Maybe it was born premature, we don't know. So maybe we have the 519th. But I would go ahead and probably say 519, but I would accept 518 as well. But it's as simple as that. Just plug in the numbers and go. Now, I do want to point out that if we're using the graphing calculator or any other similar calculator to this, let me go ahead and just get it a little bit better on the screen. So if we want to type this in here where we have 200 times 2.7 to the power of, so this calculator is actually doing the power in the same way. Let me change the mode real quick just so that some people don't have this math print mode in their graphing calculator. So let me just point out what it's going to look like there. So if we have 200 times 2.7 to the power of, at this point we do not want to say 0.08 times 12, and I want to point out why. So what I have typed is incorrect, just to be clear. And hopefully it's clear when we get this answer of 2,600, but basically that, whoa, hold on a second. That's a ridiculous number of rats when we were only getting 8% more each time. The problem here is with parentheses. If we want to say 0.08 times 12 is all in the parentheses at the same time, or sorry, in the exponent at the same time, then when we hit our exponent button, we need parentheses to say 0.08 times 12 is all in the exponent. We use parentheses to say all in the exponent, and that's how we get the correct answer there. So let's look at one more easy word problem example before we step it up just a little bit as far as the level of difficulty in our word problems. So the other topic I want to address here when talking about exponential functions and word problems is compound interest. Compound interest is a situation in which we will be using an exponential function because of the idea that we're multiplying by the same value over and over and over again. The idea of compound interest is when we have interest computed on an account, that interest is put back into the account, and then the next period that comes up later, we get interest again on that new amount. That interest gets put into the account. Now we get interest upon that. And so what happens then is if we're getting interest, like let's say you get 1% interest at the end of the year. Well, if you take your interest of 0.01 and add it to the amount that you had, which was 1, then you're basically multiplying by 1.01. Then at the end of the next year, you multiply by 1.01 again, then 1.01 again, so that every year you're multiplying by the same amount. Well, the same thing could be said as far as if it wasn't every year, if it was, every month. Well, if it was every month, then instead of 1.01, we wouldn't get the full 1% since it's only a month. So we divide by however many computations there are within the year. So if it was monthly, we would divide that 0.01 by 12, because we're only getting a 12th of that interest rate. So in this formula here, the n value is the number of computations per year. So what's happening then is your A value is the total amount of money that you're going to end with. The P is your initial amount, or the amount you start with. You're going to multiply that amount you start with by 1 point something. That 1 point something comes from taking your interest rate as a decimal and dividing it by the number of computations per year. And that way we say, this is what I multiply by each computation period. Now the nt in the exponent, n is the number of computations per year, t is the number of years. If I multiply those two things together, that's the number of computations I have. So if I take the number of years that my money sits there collecting interest times the number of computations per year, that exponent is the total number of computations. So this is a formula you should be familiar with, and you should probably memorize it. That A equals P times parentheses 1 plus R over N to the NT. Now in this portion of this lesson, we're going to deal with just doing computations of this, putting it in the calculator. Later on in the unit, we'll be solving this equation and having to do a little bit of logarithms and stuff. So anyhow, I do want to point out a couple of n values that come up quite a bit. So remember, n is the number of computations per year. So if interest is biannual, biannual means every other year. So that means n is 1/2, that we get half of a computation per year. Annually, of course, means once a year, so n is 1. Semi-annually means twice every year, so n is 2. Quarterly, of course, there's 4 quarters to a whole, so there's 4 quarters to a year, so n is 4. And monthly would be n equals 12. There's 12 months to a year. Now, if we have daily interest, for the purposes of this class, for the purposes of our calculations, we're going to agree to use 365 for n. Now I say that because there's a couple other values that can be used in other situations. If we want to be as accurate as possible for a long-term calculation, like if we want a daily interest that was compounded over 10 years, then we should probably use 365.25 to accommodate leap years. Now, the other thing that happens is there's actually a law in the United States that allows banks to use 360 for this calculation instead of 365. And really, what that comes from is before calculators were super easy to use and you use tables and things like that, 360 was an easier number to use. So there actually is a law that, and this is especially true for short term loans like payday loans, you can actually use 360 for the calculation. The moral of the story, read the fine print of whatever loan you have. So, anyhow, back to our problem at hand. We're being asked to find the amount owed at the end of 5 years if $3,000 is loaned at a rate of 10% compounded quarterly. What I expect you to do in a problem like this is I expect you to write out the controlling formula, which was at the top of our page. Then I expect you to write out each of these values, each of these variables here, put a value into whichever ones you know, and then say, what am I trying to solve for? So as we read through the problem, at the end of 5 years, 5 years is a time, so that's the T. $3,000 is loaned out. That's the initial amount that we got. So P is the initial amount. So that's the 3,000. The rate is 10%. Now remember that we always enter this as a decimal, so it's 0.10 or 0.1. The fact that it's compounded quarterly means n is 4. There are 4 computations per year. The A is our unknown. So if we plug these values in, we get 3,000, 1 plus 0.1 over 4, all to the 4 times 5 power. Now, if you want to do some simplifications here, you really could. I'd prefer not to. I'd prefer just to use my calculators for what they're good for. So I'm going to take my calculator here, and if I use the good scientific calculator, I have 3,000 parentheses 1 plus. I'm going to hit the fraction button, the n over d button. And that way I don't have to worry about, do I have my parentheses right and all that stuff. So I'm going to type it exactly like it appears. I'm going to hit the exponent button, where I can just do 4 times 5. Now, yeah, we know 4 times 5 is 20. You could type 20 if you wanted to. We hit enter here, and we get an answer of 4915. Now, I would round to the nearest cent, so we can see that it's going to be 85 cents. That makes the most sense. Ha! Since we're talking about money, sorry for the dad joke there. So since we're talking about money, our answer should be $4,915.85. That's how much is owed on our $3,000 loan. Now, of course, you want to stop and make sure this answer makes sense. So we started with a $3,000 loan. We're going to pay back $4,915 in the end. That seems reasonable for that very high interest rate of 10%. Now, if we end up with something like $30,000, we should probably say, oops, I made a mistake here. So in our graphing calculators or something that doesn't have the math print mode, let's talk about parentheses. So the 1 plus 0.1 over 4, no extra parentheses are necessary there, just the parentheses that we had written on paper. Where parentheses become necessary is in the exponent. We need to say in the exponent 4 times 5 is in parentheses to say all of that is in the top together. That gets us the correct answer. Now, without those parentheses there, I'm hoping that we would catch our error. That if you forgot those parentheses, that's when you get a ridiculous answer. We had a $3,000 loan that we need to pay back $16,000 on. That's ridiculous. So hopefully that's an error that you would catch and say, whoa, that's wrong. I don't want that. So catch our errors, think about whether our answers make sense. So the next thing I want to talk about is just to piggyback on that whole idea of compound interest. Is to say that idea that we took with compound interest, we could really apply that to a more general sense. That what was happening is we were saying, if there was a 1% interest rate, then we would take our principal and multiply, well, let me actually go a full version here. The interest of principal times rate times time would be your principal times 0.01 if your time was 1 year. And so then the final amount that you have would be to take your principal plus your interest, which would be principal plus 0.01 times your principal, which would be 1.01 times your principal. So we said after a year, you'd basically take your principal and multiply by 1 plus your interest rate. Now, if we sat there for another year, what's going to happen is we're going to multiply by the 1 plus 0.01 again. Another year, multiply by it again. And so really we said if we take your principal and take 1 plus the 0.01, raise it to the t power, where t is the number of years you've been sitting there for. That's what we were dealing with in the compound interest. Well, what if it wasn't money? We can actually apply the exact same reasoning to a generic exponential growth situation. And that's what we have typed out nicely in front of us here, is exactly what I just said about money that we've been dealing with in the compound interest. And really, we dealt with compound interest a chapter ago as well. But in general, if you have a situation where you're growing exponentially at a certain rate, then we can say, let's take 1 plus that rate, and that's our base that we're going to continue to multiply by. How many times do we multiply by it? Well, x, where x is the number of computations or the number of time periods that have passed. Now, the number of time periods needs to match up with what your rate is. And if you have an annual rate, then your time periods better match up to that. So your number of time periods need to be years. If your rate is a monthly rate, then your number of time periods needs to be months. And we're going to multiply that by your initial value. We're calling it c this time, but really same idea as before. Take your initial value, multiply by 1 plus your rate to the x power, where x is the number of time periods that have passed. I'm bringing this up because this is going to allow us to create equations out of word problems that we can then solve. So let's now look at an example of that. So this example tells us to suppose that a city with a population of 900,000 has been growing at a rate of 5% per year. And we're asked if this rate continues to find the population of the city in 10 years. So remember that our controlling equation for an exponential growth is y equals c, where c is the initial value, times 1 plus r to the x power. Let's look at what values we know. The initial value here is that we're starting with 900,000. The rate at which we're growing is 5%. This was per year. I'm going to jot that down because remember that x is the number of time periods. So I want to make sure I remind myself that yes, it was 10 years. Those guys match up. And so really then at this point, this is just a plug and chug kind of problem. We have 900,000 times 1 plus 0.05 to the 10th power. And so we're just going to get out our calculator and type that in. So 900,000 parentheses 1 plus 0.05 and the parentheses. Raise that to the 10th power, and there's your answer. So 1,466,005. So that's how many people we can expect in this city 10 years from now, is 1,466,005. So we start with the generic exponential growth equation. We figure out what values need to be plugged into each of the variables. And then in this case, we just straight up calculate. The other thing we can talk about besides the generic exponential growth is we can talk about exponential decay. So by decay, we mean that we're losing whatever it is that we originally started with. If you decay by 10%, what you want to think about in terms of mathematically to determine how much is still there is to say, if I decayed by 10%, then 90% is still there. And so that's why if we look at this equation for exponential decay, we have 1 minus r. So if we are decaying at 10, oops, if I could spell decay right would be helpful. I missed the letter there. So if we are decaying at 10%, then how much remains is 90%. So that's in that formula of 1 minus 0.1. That's where that comes from. That's why we're doing 1 minus r when we're doing exponential decay, but everything else stays the same. We still have a c value as your initial amount. We have the percent that we're decaying that we're going to use as a rate, so we use a decimal. And we got the number of time periods, and again, the time periods need to match with the rate, that if it's an annual rate, then the x needs to be in years, or whatever the case might be. So let's look at this example. We have a rare isotope of a nuclear material. It's very unstable, and it's decaying. This is a big keyword. Obviously, in the notes here, we just covered decay, so it's going to be decaying. But if this wasn't directly out of the notes, you would see that keyword decay and say, I know this is a decaying problem. I know I'm decreasing the amount that I had. So it's decaying at a rate of 11% per second, each second. Find how much isotope remains 8 seconds after 10 grams of the isotope is created. So our controlling equation here is C times 1 minus the R raised to the X power, where the initial amount we're starting with is 10 grams. The rate at which we're decaying is 11%. And again, I'm going to jot down that this is per second, just to remind myself when it comes to X, that X was, not 10, it was 8 seconds, was 8, and this was also measured in seconds, so it's matching up. And then we're just going to plug those numbers in. We're going to say 10 times 1 minus 0.11, all to the 8th power. Now, if you wanted to go ahead and simplify 1 minus 0.11 down to 0.89, you could, of course, do that. Or we could just let the calculator do it. We could say 10 times 1 minus 0.11, all raised to the 8th power. There's our answer. We're going to call it, let's say, 3.94. And that was measured in grams. And that's it. So for exponential growth, we have 1 plus r. For exponential decay, we have 1 minus r. Otherwise, the equations stay the same, that we start off with our c, our initial amount. X is the number of time periods that have passed, where that time period has to match with the time period in the rate. And for the most part, we're just going to do some plug and chug type of word problems. All right, so let's look at the last example for this lesson. We're going to talk about half-life, and this is going to fit in nicely to exponential decay, is what's happening here. Half-life is defined as the amount of time that it takes for half of a substance to decay. So half-life is a number given to us that helps us to understand the units in which the rate is being defined. That's what's really happening. Let me repeat that. Half-life helps us understand the units for which the rate is given. So as an example here, we have this isotope that has a half-life of 110 years. How much of a 19-gram sample is left after 150 years? So this is going to be an exponential decay situation. So let me write out the formula. Same formula of exponential decay as we've used before. So we've got the C, we've got the R, we've got the X. Now in this example, we started with a 19-gram sample, so that's the C, is 19 grams. Now the half-life was given to us as 110 years. What that tells us is every 110 years, we're going to end up with half of what we started with. So after 110 years, we're going to be down to 9.5 grams. Another 110 years later, we'll end up with half of that. So the rate, if we're talking about half, is we're going to decay at a rate of 50%. But how often are we doing that? Per 110 years. So this is where we need to match up the units. The rate is 50%, but it's every 110 years. So with x being the number of 110 year periods, how many 110 year periods have passed if 150 years have passed? Well, that would be to take the number of years that have passed and divide by 110. Divide by how many of those periods have come about. Once we identify that that's what's going on in this problem, it becomes as simple as the rest. We plug in the C value, we plug in our rate of 0.5, and our exponent of 150 over 110. So now we can type this in just directly as we see it. 1 minus 0.5, all raised to the power of 150 over 110. We end up with about 7.4 grams remaining. Now this should make sense that we knew after 110 years we'd have 9.5 grams left, and we had 40 more years pass, so some more decayed. Now just to point out, if we were using a non-math printy calculator, we would need to be careful with parentheses. Then we'd have 19 times 1 minus 0.5. We would need parentheses in the exponent to say this 150 over 110 is all in the exponent together. And that's how we'd achieve the correct answer without the nice math print.